Okay, I hope you have this printed out. It is called Motor Power Circuit Design for Electricians. This is going to walk us through how to select the size wire for a motor, the size starter, the size fuses and or inverse time breaker, and how to set the magnetic trip if we have one. So let's get started. I have the power circuit drawn out here. We're starting over here, okay? This is where our three-phase comes in. The NEC says we must have a way to disconnect the motor from the main supply. So you're going to have in a motor control center a 800,000 amp breaker that's going to feed a bunch of motors. And each one of those motor starters is called a bucket. It's what they're in a motor control center. This is the same layout as you have for your home power distribution panel. You've got a 200 amp breaker or 100 amp breaker coming into your home, and then that's going to break off and feed different areas of your house, like the 15 amp breaker that feeds your living room. Okay, you got to have a way to disconnect your living room and also protect that living room circuit from that 200 amp breaker. Motor control center, same thing. So we can accomplish being able to disconnect that motor in one or two ways. We can either have a disconnect, a 3-pole disconnect, and then they normally have fuses with them, so it'd be a 3-pole fused disconnect, F-U-S-E-D, fused disconnect. Or it can be a 3-pole circuit breaker for 3-phase. Either one will accomplish both of them, okay? Then we have a starter. A starter is made up of two different devices. A contactor, which opens and closes and applies your power to the motor, starts and stops it, and then a heater block, okay? Now, we have three different conditions of a circuit we have to protect from. A line-to-line short, a line-to-ground short, and overload, okay? When you have a line-to-ground short, current goes through the roof. When you have a line-to-line short, if you take an extension cord and short hot to neutral, current through the roof. Overload is when you're asking for too much horsepower off the end of that shaft. So the current for overload goes up over time. In motor circuits, we separate overload from line-to-line short and ground fault. In your home, your breaker that feeds your living room has to do all three. It has to protect you from line to neutral short, has to protect you from a ground fault, and has to protect you from overload. So Tom Henry says the code book's got a wall in it, okay? Over here's motors, and over here's everything else. So what we're getting ready to talk about only applies to motors. You calculate fuses and breakers and wire size totally different over here for everything else, okay? So your fuses and or circuit breaker gives us line-to-line short and ground fault protection. Our overload block gives us motor overload protection, okay? Now, the calculations we're going to do is good for up to 750 feet distance between your starter and your motor. So that takes care of 99% of everything we do, okay? So don't worry about distance and voltage drop to your motor till you get past 750 feet. Now, let's get started. We have a 10 horsepower motor here at 480 volts, it's 3-phase, and it has a nameplate full load current of 11.5 amps, okay? I picked that. But if you remember how to guesstimate a 480 volt motor full load current, okay? If you take horsepower times 1.1 or 1.2, that will give you a good estimate of FLA. That's estimate of FLA of 11 to 12 amps. Now, that's just a guesstimate if you can't get to a nameplate to help you troubleshoot, all right? But the nameplate on this is 11.5 amps, and let's say it's a GE motor. All motors are not created equally. So we're gonna have, if we burn up that 10 horse GE motor, we are going to go to the storeroom, and we got a 10 horse bow door, or we got a 10 horse US motor, that's what we're putting back. all your motor manufacturers will have a little different FLA for a 10 horse motor. That's just the way they make them. They have different engineers, they're gonna be a little different. So when we build this circuit here, we've got to build it for any 10 horse, 3,600 RPM motor that we put on there, okay? So we're going to table, the first steps go to this table, 43250, okay? It's in your handout. This area here that I've got marked out, you don't need that. You just need this side here, okay? It's the side that says induction type squirrel cage and wound rotor motors. So all you need is the application voltage and the horsepower off the nameplate. So it's 10 horse, okay, at 480. So this column says 460, you pick the columns closest to what you got. We got a 480, it says 460, we use the 460 column. We go over here and come down to 10 horsepower, come across to 460, and it tells us the worst case, this is the worst case full load current. So it tells us that it's going to be 14 amps. We're going to build this circuit, you might say hell for stout, so that it'll take any 10 horse motor. Now, this here, if we multiply 1.1 and 1.2, we're seeing 11 to 12 amps full load. The table says 14, so see the table's going to be a little higher. So we're building this circuit so it'll last forever. Okay, so now what we do, we go to step 2. We found 14 amps off the table. Don't use nameplate. It's wrong to use nameplate. You use the table current, 14 amps. Here it says multiply the full load current by 125%. Now, why do we do that? We are getting ready to select wire. Think about what happens whenever you start a motor. That motor is going to pull 6 to 8 times FLA, right? So if we were to do the math, we're pulling 60 to 90 amps on this circuit to start. So what's that going to do to the wire? It's going to heat it up. Now it depends on whether we have a high inertia or a low inertia load. High inertia load is going to be like a flywheel. It's going to sit there, and when you hit the motor start, it's going to turn a lot of weight. It's going to take a while to get going. Take a chemical pump or something, it just whoom. So that has a bearing on how long that 60 to 90 amps last. So it's during that time that we're going to be heating that wire up. So we have to add a 25% factor to keep that wire from degrading the insulation from starting current. Because that insulation has to last forever, right? So 14 amps times 125% equals 17.5 amps. Now 17.5 amps is what we're going to use to select wire. So we're on the step 2 page. Let's go to the next page over. And you're going to see an arrow right here. I'll tell you what that arrow says. The arrow says 14 gauge wire is the smallest wire we can pull into a motor in the real world. Okay? So we know 14 is the smallest. We're going to go to the next page. This here is our ampacity chart. This side here is aluminum. I mark it out. We're not using aluminum for motors in most cases. We're using copper, but I didn't mark it out so I can't use it. I just marked it out so it doesn't catch my eye. So we're going to look down through there, and we're going to pick the kind of insulation we're going to use. Most of the time, we're using THHN. And that is 90 degrees C wire. So THHN is in this column here, third one over, okay? Now we're going to go down till we find at least 17.5 amps. And when we look over there, it says 16 gauge wire. But what did the other page say? The other page says we can't pull in anything smaller than 14. So we got to automatically go to 14 gauge wire, okay? So, number 14. Now, we say 14 gauge wire, and that's all we say. As electricians, it's assumed to be copper. If it's aluminum, we must state aluminum. But I don't remember ever pulling aluminum into motors. I've always pulled copper. So, now, there's some double asterisks here, okay? right there for 14, 12, and 10. Those double asterisks down the bottom of the page takes you to another place in the code book. Here's what it says. Remember that wall I was talking about? Motors are over here and everything else is over here. Legally, 14 THHN, we could put on a 25 amp breaker if we had to, okay? On a motor, only on a motor. If you're out anywhere else other than motors over here, everything else in code books over here, if you see 14 gauge wire on anything bigger than a 15 amp breaker, it's wrong. Other than a motor, if you see 12 gauge wire on anything bigger than a 20 amp breaker or fuse, it's wrong. If you see 10 gauge wire on anything bigger than a 30 amp breaker or fuse, it's wrong, okay? And here's the reason for that. You remember when we were talking about the overload block? We have a separate overload block that protects that wire from burning up from overload. Then our fuses and our breaker, takes care of line-to-line short and a ground fault. So they're separated in a motor circuit. But at home, that 15 amp breaker that feeds your living room has to do it all, okay? So it's a different way of calculating. So we always need to remember that, okay? 14 gauge wire never on anything bigger than a 15 amp breaker or fuse. 12 gauge wire never on anything bigger than a 20. And a 10 gauge never on anything bigger than a 30, unless it's a motor circuit, okay? So we're gonna pull 14 gauge wire. Now, we are going to select the starter size we need. Now, all we need is the application voltage and the horsepower. So it's a 480 volt motor and it's 10 horse motor. Now, on a starter, you have to go by horsepower at the application voltage. So this side here, you don't need, that's why I marked it out. You just need this side here. You need full voltage starting. That's what we're doing. It's called across the line start or full voltage start. If we take 460, it's close enough to 480, right? Go down to 10 horsepower, and across here, it's a NEMA size 1 starter, okay? So, now we know what size starter. Now, if we were to cut the application voltage down to 230, that same 10 horse motor, if we look at under the 230 column, and we go down, we see that would take a size 2. And here's the reason. These contactors on a starter, here's contactor, here's contactor, this is a reversing starter, here's the overload block right here. These contacts are only good for so many amps, okay? So for so many amps, it's at the application voltage. Power equals current times voltage, right? P equals IE. So for the same 10 horsepower, if we cut the voltage in half, the current has to double. Power, current times voltage. So the higher the application voltage, the lower the current, okay? And a smaller starter for the same horsepower motor. So, now we know we need a NEMA size 1 starter. Now we move to the next step. We're going to identify what size fuses or breaker we need for this. This comes off of table 43052 right here. Now, I marked this part out here. You don't need that. You just need the top 2 rows. The top row is single phase. This is 3-phase motor. The second row says AC polyphase. Poly means many. So that's a 3-phase motor. Now, we're going to take this one step at a time, okay? Now, we have one-time fuses. We have dual time. And the fuse that's made for motors is a dual time or a time delay or a dual element fuse. They're all the same. That is made, remember when your motor starts, you got that motor current running through it, it's gonna be heating the wires. It's gonna be heating the fuses or the circuit breaker too, you know? So, they make dual element fuses for motors. One-time fuses are not made for motors, but we could use them if we had to. And I'm gonna show you how here in a minute. First thing we're gonna do is a dual time fuse. If you look here, it gives you multipliers for your full load current. If we go back to 43250, 14 amps is our worst case full load current for run current. This here says for a dual element fuse, if we multiply 14 amps times 175%, that's going to give us the figure we need for our dual element fuse. So that comes out to 24.5 amps. Okay, I'm going to get rid of this right now. Now, we're going to add another step in here. 24.5 amps, they probably don't make it. What this next page right here says, it says that we must select a fuse that the code book considers is a standard size fuse or circuit breaker. So 240.6 gives us a whole list of standard size fuses or breakers. Now, one favorite trick question for electrical licensing is 601 amps a standard size fuse? If you look through here, you won't see it in the list, but down at the very bottom, read that last sentence, okay? That last sentence says, additional standard ampere ratings for fuses shall be 1, 3, 6, 10, and 601. So 601 is standard size fuse. Don't know why they did that, but they didn't call me either, okay? So, our calculations took us to 24.5 amps. If we look at 240.6, we gotta find 24.5. They don't make 24.5. But what the code says is you could go to the next standard size higher than your calculation. So the next size up from 24.5 is 25 amp. They make a 25 amp fuse. So we took 14 amps times 175%. They gave us 24.5. Then we look at our chart here. 25 amp fuse is what we need for a dual element, okay? So let's say that it's midnight and you blow fuses going to this motor. You change the motor out, it's burned up, and you don't have dual element fuses in the storeroom. The code lets us use a different multiplier for a single element fuse because they're not built to overlook the starting current. So the multiplier for a non-time delay fuse or a single element or a one-time fuse, it's all the same, is 300. And 300% times 14 is 42 amps. Now, 42 amps, I can tell you, it's not a standard size fuse. So if we look over here and we look for 42, I see a 45. So we can use a 45 amp one-time fuse and still protect that motor circuit. So at 2 in the morning, if you need to put fuses in that motor to get it going because it burned up, you changed it out, it blew the fuses because it went to ground, then you don't have any more 25 dual elements, you could do the math, get 45 amp single time fuses, single blow, single element, and put them in there. Now, a footnote. To do this right, you've got 3 fuses, right? To do this right, you would change all 3 of them out to non-time delay. And then the next morning or whenever you got the right dual elements in, you put all 3 25 amp dual elements in instead of having 2 of one and 1 of another. So change all three is the correct way to do it. Now, you're gonna find everything out there, but I'm telling you the right way to do it. They all have different time current curves. You should change them all out together, even though you have one or two good ones left. Put all three non-time delay in, and then when you get the dual element replacements in, change them all three out and put 3 dual elements in. Right way to do it, okay? Now, let's say you have a circuit breaker instead of fuses. That's my favorite. You have a motor goes to ground and trips your breaker. You can reset your breaker once you change your motor and you're in business. You don't have to go to the storeroom. You're not always buying fuses. Okay, so a circuit breaker has a multiplier, inverse time circuit breaker, and it's on this chart here, okay, of 250%. And 250%, okay, let me write this down, inverse time breaker. So 250% times 14 is 35 amps. Now, if we look over on the next page, 35 amps is a standard size breaker, so we don't need anything else. We put a 35 amp breaker in there, we're good to go. Now, you're gonna see under inverse time here, where my finger's at, it says 250Z. I spent a lot of time tracking that down. I did not know what the Z meant. I know Z stands for impedance, but it didn't make any sense for a multiplier for a breaker. I looked and looked and looked and looked. Finally, I called someone with the NEC, and that is a typo. You would not believe how many electricians have hunted to try to figure out what that Z was. It ain't nothing, it's a typo. So it's 250, 250%. Now, if you have a breaker, let me show you one. I've got one here, dadgummit, I saw it a while ago. Okay, if you have a breaker that has a little adjustment here, okay? That little adjustment is a magnetic trip. Your regular circuit breaker is going to trip in 6 to 8 cycles, okay? In time, 6 cycles on 60 hertz power distribution is 1/10 of a second. So 0.1 to 0.15 seconds is the time this thing's trying to heat up to trip. Tens, if not hundreds of thousands of amps is going through this in that 1/10 of a second. 1/10 of a second at 186,000 miles per second is 18,600 miles of electricity that gets through here before it trips. That's a lot of electricity, right? So the magnetic trip will take us out in 1 to 2 cycles in a lot of cases. So we're going out in 1/3 of the time with the magnetic trip. A magnetic trip doesn't have to heat up. It just looks for that current spike. So the multiplier for it is 800%. So we take 14 times 800%, and that's mag trip or instantaneous trip, same thing, and that is 112 amps. Now that might sound like a lot, 112 amps. Wow, that's so much more than 14 wires is good for, right? Sure it is. But what's the job of the breaker or the fuses? It's line to line short, line to ground short, okay? So when that happens, instantly that current goes through the roof. You blow through 112 amps so quick, many times quicker than you can blink an eye, okay? 1 to 2 cycles, that's gonna trip, okay? So it makes sense whenever we split the overload protection out for the overload heater block, okay? All that has to do is take care of line to line short, line to ground short, okay? So 112 amps, is that a standard size? Nope, so we go to 125 amps. And that'll be a setting. That magnetic trip current will be a setting on the front of the breaker that you'll just turn a little notched dial, or sometimes it's not notched. So you'll just set it as close as you can to 125 amps and you're good. Okay? So now, we've determined what size wire, what size starter, what size fuses and or breaker, and how to set our instantaneous overcurrent. Now, step 6. Now we are going to determine how to size our heaters. Our heaters, this here is a reversing starter, okay? Contactor, heater block, where my hand's at. These 3 places here have heaters. This is where we custom fit the overload protection to this motor, Everything we've done up to now has been for any 10 horsepower motor we hook to this circuit. Now we are going to say we have a GE motor with a FLA of 11.5 amps. This is the first time we've done this, okay? We're going back to the nameplate and get what this motor draws, okay? So, now we're going to deal with our overcurrent, our overload protection. And remember, overload, it means when we ask for too much horsepower off the end of that shaft. Now, it's right here, it says separate overload device. What this says is, if you have motors that's marked with a 1.15 service factor or greater, most motors are a 1.15 or 1.2 or 1.35, or 40 degrees C rise over ambient or less. Now what that means is the 40 degrees C, that's how hot that motor runs when you're developing horsepower. So sometimes they'll call you and say, hey, this motor's so hot you can fry an egg on it. Well, if it is 100 degrees on a summer day and that motor is a 40 degrees C over ambient, yeah, you can fry an egg on it, but the motor's built for that. That same motor, if you go out there whenever it's 0 outside, 40 degrees C over 0 is a pretty good place to set on to warm up, you know? So just know that's 40 degrees C over ambient. A good way for me to look at a service factor of a 1.0, if it's a 10 horse motor, is 10 horse motor. But a 1.15 is really 115% of a 10 horse motor. Or a 1.35 is 135% of a 10 horse motor. It's the higher the service factor, the stouter the motor's built, the more rugged it is, okay? So, what we're gonna say that this motor has a 1.2 service factor, okay? 1.2 SF, and it's a 40 degrees C rise over ambient. Either one of those two, and we go to 125% of our full load current, okay? So, if we take 11.5 here and multiply it, I'm going to erase this here so we can have a little room. If we take 11.5, now that's nameplate current, times 125%, we get 14.375 amps. Now, the code says that we select motor heaters because these 3 little things here, we unscrew, pull them out, you get 3 of the right ones and put them in. And that custom fits this to your motor. Most electric shops will use nameplate current. They'll use 11.5 amps. This is so important, so important. 11.5 amps when they should be using 14.375. Now most equipment is over-engineered, which means you got more horsepower than you need, okay? So, if you select heaters at 11.5 amps, you're only asking for 80% of the horsepower out of that motor. In other words, this overload is going to trip out at 8 horsepower off the end of that shaft instead of 10. Okay? Give or take, all right? Why is that important? Well, everywhere I've ever worked always wants to run more and more on a given piece of equipment, or wants a pump to run harder, or pump stuff you've never pumped before. If we know this as electricians, and we look at that starter right here, and we get those numbers, and we look it up on a chart, you gotta have a heater chart, not getting into that right now, and we see that this motor had 11.5 amp heaters in it, we could calculate that here for 14.375 amps, change those heaters out because it was tripping out because they're trying to pump stuff that's too heavy or heavier than they normally pump. We can bump those heaters up to 14.375 amps and it may run just fine. And you still have motor protection. But now you're using the full 10 horsepower of motor, because all this knows is it's going to trip out when those heaters get too hot. So it's up to us, you, me, to size these heaters right so that we can get full horsepower off the end of that shaft. Most of the time, if you just go straight by nameplate, most equipment's fine with that. But I've checked with motor shops and they verified this. They said most motors, whenever you use nameplate, most motors, you're asking for 80% of the horsepower. So we've got 20% left according to the NEC. Now, there's a difference. Remember us talking about starting current? It depends whether you have a high inertia or a low inertia load. A high inertia load like a flywheel. Low inertia load, you start a motor, boom, and it's running. A high inertia load, it's the flywheel. You hit start and it's turning faster and faster and faster and faster. Then it gets up to speed. So the amount of time that your starting current lasts matters with the load. So let's say that you size it with 125% on this particular motor and you're getting nuisance tripping. You take an amp clamp out there, you're not pulling too much current, you're just staying in starting current too long. The next page here on the handout says that we can go, instead of 125%, we can go to 140% of nameplate, and we can go from 14.375 to 16.1 amp heaters, okay? And still have motor protection. So, if we know that, we can do a whole lot of troubleshooting with our own noggin instead of changing motors out, right? So, if you don't know this, and let's say that you're on a production line and they're trying to run material that's heavier than normal. If you don't know this and you say, well, the motor's tripping out all the time, we just don't have a big enough motor. Well, let's put a 15 horse on it instead of a 10. Well, a 15 horse is not going to bolt up to the same bolt hole patterns as a 10. So you got to change out the base. Then it's not going to bolt up to the same gearbox. Now you got to get a new gearbox. Then you got to take a jackhammer out the base and all that other stuff. But if we know this, all you got to do is calculate, change out 3 heaters, and you go from 0 to hero. Okay, so it pays to understand motor circuits. So I hope this helped. That's got us through motor power circuits. I will have another video on selecting the size conduit and conduit fill. And email me any questions. Take care, stay well.